Listen to part of a university lecture by a professor of physics. My next topic I'm sure will interest all of you. I want to talk to you now about black holes. Simply speaking, a black hole is what's left after a large star dies. You're already aware that a star is an energy producer, a nuclear fusion reactor. Its core is a gigantic nuclear fusion bomb that's trying to explode. But its mass of surrounding gases is so large that its gravity contains the explosion, and the balance that exists between the gravity and the fusion is what determines the star's size. However, as a star gets older, as it ages, its fuels get used up and its nuclear reactor slows down. And then its gravity gets the upper hand. The star implodes. Gravity pulls inward and compresses the stellar material into the star's center. As it's compressed, the core heats up tremendously, and then, at some point, a supernova, a great explosion occurs, and the stellar material and a lot of radiation are blasted out into space. Only the extremely dense, extremely massive core is left. Its gravitational field is so strong that nothing can escape it, not even light. So it disappears from view. It's black. It's now a black hole. Now, the idea of a black hole, an object with so much gravity that it won't let light escape, was first proposed more than 200 years ago in 1795 by a French mathematician, Pierre Laplace. He used Newton's gravitational theory to calculate that if an object was compressed small enough, it would require an escape velocity of almost 300,000 kilometers per second, the speed of light. More recently, the name of Stephen Hawking, the great British physicist, has become synonymous with black hole theory. A black hole consists of two parts, a singularity and an event horizon. Its singularity is the point where its gravity is indefinitely strong and its mass is indefinitely dense. And this point is theoretically at the center of the black hole's core. And its event horizon is the perimeter around the core at the distance where its gravity is still strong enough to pull light into itself, at the distance where escape velocity equals the speed of light, and where nothing can escape its pull. Both the singularity and the event horizon are intangible, of course, but both of them can be calculated mathematically. The distance of the event horizon from the core is called the Schwarzschild radius, and this radius is equal to 2gm divided by c squared, where g is Newton's gravitational constant, m equals the mass of the core, and c equals the speed of light. Even though we can't see them, black holes do exist, and we can prove their existence in three basic ways. One way is to search for celestial objects that are very small, but that have a very large mass. For example, the astronomical feature called M87 is only about the size of our solar system, but it weighs 3 billion times more than our sun. So it's a good bet that M87 is a black hole. Another way to find a black hole is to search for matter that's accelerating, because a black hole accelerates anything that approaches it. As the matter gets sucked in, it speeds up and heats up, and this superheated matter produces X-rays, which can be detected. The star Cygnus X1 is a strong X-ray source, so there is a good possibility that there's a black hole in its neighborhood. And finally, a black hole can be detected using Einstein's theory of relativity, which tells us that gravity can actually bend space, warp space. An object with a lot of gravity located between Earth and a more distant star can bend that star's light like a lens or a prism does. This is called the gravitational lens effect. In 1996, a gravitational lens passed between Earth and Macho 96 BL5, and the temporarily brightened image was photographed by both the Hubble Space Telescope and ground observers. Black holes are a bit frightening, but if the idea of a black hole sucking in the rest of the universe upsets you, let's put them into perspective. A black hole doesn't suck in everything in sight. It only affects nearby material. If a black hole with the same mass suddenly replaced our sun, then its Schwarzschild radius would be only 3 kilometers compared to our sun's radius of 700,000 kilometers. And since Earth is 150 million kilometers from the sun, it would be in no danger of being sucked in. Without the sun, though, Earth would be very cold and lifeless, I'm afraid.